Okay, we're going to start chemical bonding, and it all starts around the octet rule. Elements tend to gain, lose, or share electrons to acquire a full octet. Unless they're in the first energy level, the first energy level is 1s2, so they only need 2 electrons to fill up a complete sublevel. If you're in energy levels 2 through 7, you will need 8 valence electrons. So sodium right here is 1s2, 2s2, 2p6, 3s1. It would rather lose this 1 electron and end up with a complete octet. Chloride ends up 1s2, 2s2, 2p6, 3s2, 3p5. So it would rather gain 1 electron to end up with 3p6. Therefore, it has a complete octet like argon. Remember, the metals are found on the left side of the periodic table. The nonmetals are found on the right side. The charges then they end up getting, group 1A is +1. Hydrogen can also be -1. Group 2A is +2. The D block is going to be between +1 to +4. +3 for group 3A, +4 for 4A. Tin and lead can also be +2. Group 5A is -3, 6A -2, 7A -1. The D block cations, these elements lose electrons from their highest sublevel first, from the S sublevel. So iron, for example, is 4s2, 3d6. Iron +2 will lose the 2 electrons from the 4s first. Iron +3 will lose 2 from the 4s and then 1 from the D sublevel. Ionic bonding. Metals transfer electrons to nonmetals, and the two form a bond due to electrostatic attractions between them, a positive charge and a negative charge, opposite charges attracting. Remember, we call positive ions cations, negative ions anions. So sodium, I showed you earlier, is going to lose an electron to become stable, and chloride is going to gain an electron to become stable. Then we have opposite charges attracting. Lattice energy is the energy required to break 1 mole of a solid ionic compound into its individual gaseous ions. It's endothermic. Conversely, the opposite would be exothermic. So for example, if I want to break this bond right here, I'm going to have to add energy. Matter of fact, I'm going to have to add 788 kilojoules. Conversely, if I flip this reaction, if I take sodium ion and chloride ion and produce sodium chloride, it's going to release that same amount of energy. So this would be endothermic to break a bond, exothermic to form a bond. Factors that affect lattice energy. There's this equation right here. You don't need to know this, but the energy needed to break a bond is equal to some constant K times Q1 times Q2 over D. Q stands for charge, D stands for distance. Basically, you just need to know this. Lattice energy depends on the distance between the nuclei and the charge of these ions. Are they +1 or +2? Are they -1, -2? The farther apart they are, the easier it is to break the bond. So the less lattice energy is needed. For example, lithium fluoride and lithium iodide. Which one requires more lattice energy? This is +1, this is -1. This is +1, this is -1. So it has nothing to do with the charges. However, iodide is a big atom. Fluoride is a tiny little atom. So these two are closer together. These two are farther apart. So therefore, it's going to require more energy to break this bond right there. Magnesium chloride and magnesium oxide. Magnesium's +2, chlorine's -1. Magnesium's +2, oxygen's -2. So this has two greater charges, +2, -2. So therefore, this one would require more energy to break that bond. Sodium fluoride is +1, -1. Magnesium iodide is +2, -1. This has a greater charge. It also has larger ions. Therefore, this one would have the greater lattice energy. Properties of ionic solids. Most ionic solids are white powders. They have very high lattice energy, high melting points. They're all solids. Okay, they have cleaves along the planes. That just means if you ever break open a a rock formation and you see a bunch of cuts into the formation, that's what it would look like up close. Ions are soluble in polar solvents. They conduct electricity. They're electrolytic. The higher the concentration, the more electrolytic they are. Okay, covalent bonds. One atom shares electrons with another atom so that they acquire full octets. This usually occurs between two nonmetals. Remember, ionic is a metal and a nonmetal. Covalent is going to be a nonmetal and another nonmetal. Electronegativity and bond polarity. The larger the difference in electronegativity, the more ionic it is. The smaller the difference in electronegativity, the more covalent it is. There's this kind of gray area in between the two, okay, where it's slightly ionic, slightly covalent. We call polar covalent. I'll show you that in a second. This right here, if you'll notice, fluorine is perfectly sharing electrons in perfect harmony. We call that covalent bonds. This is a give and take. Sodium gave fluorine an extra electron, okay, and so this took, this gave. That's the complete opposite of sharing, so this is called ionic. This right here is sharing, but fluorine right here is kind of dominating this relationship a little bit more. So this is called a polar covalent. This would be the gray area. Notice that if I take 2.1, the electronegativity minus 2.1, the electronegativity difference is 0. Okay, this is perfectly sharing, so this is completely covalent. This one, 2.8 minus 2.1, has an electronegativity difference of 0.7. So this guy is kind of dominating the relationship of sharing the electron here. So we call this polar covalent. 3.5 minus 2.5 is a difference of 1.0. This is also polar covalent. Lithium fluoride is 4 minus 1, which is 3, which is a large difference in electronegativity, therefore it is considered ionic. Molecular compounds, two or more nonmetals bonded together to form a compound. Bonds between atoms are covalent or polar covalent. Alright, we're going to start drawing Lewis structures. That's when you start connecting the dots. We will use these only for covalent compounds or molecules. They provide visual representation of location of atoms. You must know how to use these in order to predict the shapes of the molecules. That's going to be the next video. So if we're doing PCl3, you need to count the total number of valence electrons in the molecule. Phosphorus is supposed to have 5. Chloride is supposed to have 7. Of course, there's 3 of them. That would be 21. 21 plus 5 is 26. So you're going to show me 26 valence electrons. Put the least electronegative atom in the center. Phosphorus is less electronegative than chlorine. And connect the terminal atoms to it with single bonds, which represents 2 electrons. 2 electrons, 2 electrons. Except for with hydrogen. Hydrogen is the only one that only needs 2 electrons, and that's it. Okay. Now we're going to complete the octets for all the terminal atoms except for hydrogen atoms by adding in some electrons. And that is still not finished, because if you'll notice, if you add up all of those electrons, we have 8 here, 8 here, 8 here. That's 24. We needed 26, so you're going to add 2 more right here on the center atom. Count the total number of valence electrons for carbon dioxide. Carbon has 4, oxygen has 6 times 2. That's going to be a total of 16. So I'm going to put 2 here, just a single bond. Now I'm going to complete it by completing my octets over here. Now, notice, however, carbon does not have an octet. It's got 1, 2, 3, 4. That's going to be a little problem. Okay? We have enough electrons. Everything's fine. We do not have extra electrons. But carbon's octet is not full, so we're going to go to step 5, which says this. Make multiple bonds to complete the octet on the central atom. Here's 2 electrons, here's 2 electrons. We're going to move them over here so that carbon now will have a complete octet. When we do that, that will form a double bond and a double bond. Sometimes you might see triple bonds. That represents 6 electrons. If you're making a Lewis structure for all polyatomic ions, you must take the overall charge right here into consideration. So when you add this, there better be an overall charge of -1, which means there better be an extra electron in there.